Now, having discussed the electric field of a single point charge, we will see how to find the electric field when we have multiple point charges. So consider this figure where I have 3 point charges, Q1, Q2, Q3 in the XY plane, and I want to find the electric field due to these 3 point charges at some point P here. Now, the tool or the idea that we use, the principle that we use in doing so is something called the linear superposition. Linear superposition here means that we find the net electric field due to these 3 point charges at this point P, we find the electric field due to Q1 assuming that Q2 and Q3 do not exist. Then we find that of Q2 assuming the others do not exist, and we find that of Q3 assuming that the other two do not exist, and then we add them up linearly. But since they are vectors, then this will be a vector sum. So this is the idea of linear superposition. Now graphically, Q1 is positive, Q2 and Q3 are negative. So we know that, for example, Q1 in this case will have the electric field directed along the positive y-axis, as you can see from here, and whereas Q2, because it's negative, the electric field will be towards Q2, so this is E2, and the same applies for Q3, which is a negative charge also. The electric field will be towards Q3. Okay, so these are the 3 fields. Now the net electric field, or resultant electric field resulting from Q2, Q1, Q2, Q3 at this point P is the electric field that you will get when you add up these 3 vectors together, and this is the electric field due to these charges here. Algebraically, we express this using this expression. Here I runs from 1 to 3. As you can see, Qi is referred to Q1, Q2, Q3. Ri is the distance, so R1 is this distance, R2 is this distance, R3 is this distance. Now Ri hat is the vector that, the unit vectors R hat. R hat 1 is a vector that goes, unit vector that goes from Q1 towards P, so it's in this direction. Now since Q is positive, then R hat to E1 is along R hat 1, as we have discussed earlier. Whereas, for example, for Q2, this is R hat 2 will be in this direction. So it's going from Q2 towards P, but since Q2 is negative, then its field is against R hat 2. And the same applies here. R hat 3 goes from Q3 towards P, so it's in this direction. It's directed to the left, but since Q3 is negative, the electric field of Q3 at P is opposite to R hat 3. So this is how you find the electric field of multiple point charges. Check this checkpoint so that you apply what we have just said. Now we will illustrate both finding the electric field of a single point charge and the net electric field of 2 point charges by considering a specific example. It's a general example actually. In this example, I have 2 oppositely charged point charges that lie along the x-axis and at the distances A and B, as you can see in the figure. I want to find the electric field due to these 2 point charges at a point P along the y-axis. So this I will be applying what I have learned. Then I will specialize to the special case when the charges are equal in magnitude but opposite in sign, and they are and in this case I will take the distance, I will take them to be at equidistance from the origin, and so in this case the y-axis will be passing through the middle point. Now in this case we will have when the charges are equal and opposite, we will have what we call an electric dipole. Electric dipole is 2 equal and opposite point charges that are separated by some distance. So I will consider finding the electric field of this dipole at a point along the y-axis, which the y-axis now will be in the middle point between them. And then I will consider the limit of this electric field of this dipole here when this y, the distance here, this distance is much larger than the separation of the two charges. This is will give me the electric field of the dipole at along a line that is vertical to the dipole at far distances far from the dipole. We will do these in detail now.